Okay. So welcome back. So this is now module 5. So we're really halfway into the class now. I just want to briefly take a second to look back at what we have discussed already. So we talked now about essentially what data is. We talked about how to display data. We talked about what actually the relationship between populations and samples is, why we're actually looking at samples, and why that is actually relevant in the understanding of dynamics in populations. We talked about probability distributions, where basically our knowledge of probability basically translates into the understanding of how to characterize the normal distribution curve, and how to characterize the frequency distribution in terms of probabilities. But the central limit theorem basically allows us to quantify probabilities based on distributions. So today we're going to carry this a little further. So then we talked about probabilities and diagnostic testing. So that was the very practical topic last time. So in this class, we basically talked about how to use diagnostic tests, how sensitivity, specificity, and predictive values are being quantified, and how you basically have to understand them when you read about the predictive accuracy and predictive quality in diagnostic testing. We talked about receiver operating characteristic curves, which is a way to quantify diagnostic accuracy in diagnostic testing, and in setting diagnostic thresholds for decision-making, clinical decision-making when it comes to diagnostic testing, which is a super important topic. Essentially, you did then some a practice lab that basically characterized simulated data, where you were able to kind of bring your knowledge into practice, where you quantified receiver operating characteristics curves and quantified diagnostic accuracy in your data. So today we're going to go a little further into the topic. So we're now back at the normal distribution curve. We're not talking about diagnostic testing anymore. We're going back to the normal distribution curve, which is the underlying assumption of every test that we're discussing this semester is a normal distribution. We're not talking about non-parametric tests. Well, we do with the chi-squared, but that's a different conversation. That's a different test altogether. But basically, we're looking at the normal distribution, which, remember, this is symmetric, bell-shaped, and it has basically one mode. That means it has one peak, right? It has a very characteristic curve, and the most important thing is it's symmetric. So we learned about standardization, and we know that we basically can, with the normal distribution curve of a population, we can characterize the normal distribution as per the variability of it, which is the width of its span, the width of its wideness, in terms of standard deviation. And in terms of standard deviation, we can then quantify what proportion of the population is basically within a certain number of standard deviations. When we translate this now using the central limit theorem, where we're relating the distribution of a sample to the distribution of a population, we can utilize the central limit theorem to quantify the variability of possible sample means that were drawn from the very same population with a known variability. So we know now approximately if we're drawing 100 different samples of a certain size from a population, we know what the mean estimates of each sample will look like, and we know how much variation there will be around that mean of means. Then we assume that that sample of interest that we have actually really drawn, that is the mean of means, and then we want to know what's the inaccuracy, this uncertainty around that mean of that sample that we have at hand. And based on this uncertainty, we will quantify then, is this different from the population mean? Or is this different from any random reference value we're interested in? Now, this is what hypothesis testing is, in essence, in its purest form, when you compare a sample to a population mean or a reference value. And this is what we're going to do now. So first, we need to understand what is a confidence interval, because a confidence interval is essentially the underlying estimate of the uncertainty that you have around your estimate of the mean from your sample. That's what you're quantifying. You're quantifying that interval within which you are certain, with a certain confidence, that you're not wrong when you say this is different. So you're quantifying with a confidence interval, an interval within which you're 95% certain your population mean should be contained in, if your sample is indeed a reflection of your population. Okay, let's have that sink in for a second. So we have a population which is all the blood pressures in New York City. We're drawing 100 people out of this. We're quantifying these 100 people's blood pressures, and we're calculating a mean of that population. Then we have a certain variability of that population. And we're assuming now that the variability is reflecting the variability of the population. And based on our mean estimate, we're quantifying now the sample distribution, our frequency distribution. We're assuming this is a probability distribution. And based on this variability, we're assuming that there's a certain probability that this sample is actually reflecting the population mean. So we have a certain interval now, which is the confidence interval, where we're saying we're certain with 95% confidence that our population mean should be in there, based on the sample size, based on the variability that we have observed, and based on the characterization using the standardization, using the set scores. Good. So now this 95% confidence interval gives us this confidence. If we're comparing this now to an actual population mean, let's say colleagues in the past have quantified every blood pressure of every citizen in New York City, and they come up with a blood pressure in the overall population of New York. You're looking now at the mean of your sample of 100 people, and the confidence interval does not contain that population mean that your colleagues have assessed. You are 95% certain that your sample is not a reflection of the population of New York City. That is the reflection.
Reflection.
No, it's not a reflection. If it's different, if that 95% confidence interval does not contain that population mean, it's different. It comes from a different distribution. That means that you have maybe chosen a convenient sample only, and you have only measured people on Lexington Avenue here in front of 35th Street.
So if we have different means, like
if the mean is different, exactly. Exactly. So you have the mean. The mean is likely to be different. It's virtually impossible. It's like if you have a really large sample, the mean gets closer to the population mean, because you're just drawing from more and more of that population distribution. If your small sample is different, you want to find out, is your sample significantly different from your population mean? And the 95% confidence interval is a way to quantify that, because you're showing how far is that away, and is your interval, your confidence interval, containing that population mean? And that's a set test. That's a one sample set test, which is the simplest hypothesis test. So you're basically quantifying the probability that this population mean is indeed different from your sample mean. You're estimating it the other way around. If you quantify a p-value, you're actually quantifying the probability that this is actually from the very same distribution. So you're basically, the smaller that distribution, you're lowering the risk of making a wrong assumption by saying this is different. So you're quantifying the type 1 error, but we get to that later. The p-value is actually a numerical reflection of your type 1 error, where the type 1 error is the decision that you take to assume it's a different distribution. It's actually significantly different, but you're actually wrong. That's a type 1 error. So it is identical. It is the same distribution. Or the type 2 error is where you're not seeing that's different, but essentially you should have seen that difference. And it's actually wrong to say there's no difference. And that's actually, the type 2 error is particularly important when it comes to clinical trials, because this is a reflection of how well powered your study is, because if you have an underpowered study, you're more likely to not see a difference because you see more variability, and thereby you're less likely to reject your null hypothesis and to assume that there's a difference. That's where this intertwines. So,
Professor, sorry to interrupt, but I'm not sure if you're sharing slides right now. If you are, we can't see
Yeah,
them.
we see the schedule of classes on the syllabus.
you see the syllabus? Yes, yes, yes. No, I was just giving a general statement. So
Oh.
Okay, making sure, because
Thank you.
I was just talking ad hoc in a way.
okay, making sure.
I was not yet showing the slides. So the slides will be more structured. I was just giving a brief intro into what we're doing with the confidence interval. But thank you for raising your hand. I appreciate that. Okay, can you see the slides now?
Yes.
Okay, good. Okay, let's go into this. I will turn off the camera though, because well, I can leave it on, but I'm not super photogenic. So I'm turning it off if you don't like. Okay, so, but you're seeing the slides now. Okay, so let's go into it. So this is what we're discussing today, and then we're moving on to actually hypothesis testing, where we're comparing two samples against each other, which is in the end of the day what you're doing when you have cohort studies or randomized cohort studies. Okay. Okay, sampling distributions. We briefly discussed confidence intervals, what we're doing, and today we're also going to talk about the t-distribution. So basically, when you have a set test, with a one sample set test, you have one sample and you're comparing it to a reference value, or you're comparing it to a population mean. The most common case is you're comparing it to a population mean. And this is what we're doing today. So at the end of the day, you have a null hypothesis where you assume that your sample mean is not significantly different from your population mean. And you have an alternative hypothesis where you say your sample mean is indeed different from your population mean. So you're sensing this difference. That's what you're quantifying. And your p-value, which is the resultant, is actually high. Is actually your type 1 error risk, that you reject something and you actually should not have rejected what you reject. So the difference now between a set test and a t-test, so we have looked at the set distribution already with the set score table. So we know already the set scores, that's basically the distance of any point on the normal distribution expressed as the number of standard deviations that's located away from the mean. That's the definition. The t-distribution is in essence, it is the same thing, but it is an approximation of the perfect normal distribution with an mathematical manipulation, where basically you mean to make the t-distribution wider, but you're quantifying it based on a standard deviation of the sample per se. For the set distribution, you need a population standard deviation. So you need the actual standard deviation of the population of New York City. Whereas for the t-distribution, you can approximate your distribution variability from the population using the variability in your sample. And that mathematical operation is manipulation is actually quite minor. And we will see how this is manipulated. But it inflates because the population distribution will be wider, there will be more standard deviation, whereas the sample is smaller because you have a sample, therefore you have less variability. In a population, you have like the universe contained, therefore the standard deviation is going to be wider. Good. So, but now let's go back to the central limit theorem. So the population is extremely wide, and that's the population of US in terms of cholesterol levels. That is the central limit theorem relating now the sampling distribution to your population distribution. So it's narrow. And you know now that the mean of the population and the sampling distribution, so the sample mean is identical. That is what you assume. If it were a perfectly drawn sample, should be, right? It's like you draw a random sample that is perfectly random from your population. That mean blood pressure should be exactly the same as the population mean blood pressure. It's unfortunately in most cases not. And this is what we're going to do today. We further know under the central limit theorem that the standard deviation that you have from the population relates to the variability of and the uncertainty of your mean estimate by a relationship that is basically standard deviation divided by the square root of the n, gives you that standard error of the mean. So that's the variability around each mean estimate. So you have one mean, that is your sample, those are your 100 people. And now you assume, based on the variability you have of the population spread, which is sigma, you can estimate now how much would you expect a mean estimate to vary around all mean estimates. That means if you draw 100 different samples, each of them 100 people, you get different means with each sample. And you assume now that that variability of all these sample means will basically now relate to the standard deviation of the population, the sigma, which is there's more variability if there's more variability in the population, logically. And if your sample is larger, then this denominator will get larger. Thereby, your resulting variability of those mean estimates is going to be smaller. Because the larger your sample, the more likely your mean in the sample will reflect the mean in the population. That's the simple principle of the central limit theorem. And then if you have a larger n, that will lower the standard error because it basically increases the denominator. We talked about that. Sample mean is more likely to fall closer to the population mean, and it's more likely to be normal distribution. So now we have, in addition to that, we have with proportions. Same principle applies with proportions. A proportion of a population is, let's say you have 10% diabetics in a population. You basically, you draw a sample of 100 people. The first sample has a distribution of 11 diabetics. So there's 11 diabetics in there. The second sample has 8. The third sample has 13. The fourth sample has 7. So you get a certain estimate and you get a certain variability of that estimate of how many diabetics are in your samples. This distribution of these uncertainties essentially create another distribution, which again can be approximated in what is called the normal approximation of proportions. And you're estimating now that standard error of that proportion estimate by quantifying this as P. That's the probability of a diabetic being in your population. If you know the prevalence to be 10%, this is 10% or 0.1. If you have 1 minus P, that's your Q, and 1 minus P is now 1 minus 0.1, so that's 0.9. Dividing that by the size of your sample basically gets you to a standard error of your proportion. So this is how you can calculate it, and we're doing this today. So that's a nice exercise how you basically can estimate whether your proportion is significantly different from another proportion. And we're comparing this today to population values. For a random sample of size n from a population having mean mu and sampling distribution, okay, we talked about this. And now when it comes to confidence intervals, so point estimate is one mean estimate. So that's my sample of 100 people, that basically has one mean estimate. If I have 100 samples with each 100 people, I have 100 different mean estimates that are building basically a distribution of estimates. That's the distribution of means. So if I have an interval, I basically have an interval of two numbers. So that becomes an interval estimate. So the confidence interval is a mean estimate. Now, why is it a mean estimate? Because if we are looking at a random sample of 309 infants, and we know now the standard deviation from the population to be 18.2, we can now use this to quantify that confidence interval around our mean estimates of 119 ounces, 119.6 ounces, to compare this to the overall population of infants born. So if we had now, and this is the distinction. So if we have standard deviation of a population and we want to quantify 95% of that population that falls into this interval, that would be 2 times the standard deviation, right? We talked about this, but this is if you have an overall population. So for a sample, you're basically resorting to a distribution of means and the standard error of the means. So you're quantifying a probability within which you're 95% certain you should have your population mean contained in. So if we were to calculate this now, we would need to use the same set-score distribution that we have had for the normal distribution, which is the set-score table that was in an earlier class. And if you remember, I pointed out back then minus 1.96. So 1.96 is where you capture basically that point to the left of which you basically have 2.5% of your population on the left side of your normal distribution. To the right side, you basically have 2.5% to the right. You remember this is 2.5. And here you have 0.975, which is basically, that's plus 1.96. There you have 2.5 to the right. So that together is 5%. So now 1 minus 5% gives you 95%. Therefore, you can now quantify your 95% confidence interval with minus 1.96 and plus 1.96. And you get the lower limit of the confidence interval, and you get that upper limit of the confidence interval. Using the standard error of the mean characterizes your distribution of the sample means. So you have those sample means, you have those 100 different sample means that are distributing with the standard error of the mean. That gives you that probability, that variability. Characterizing this now with the standard error of the mean, so 1.96 times the standard error of the mean left to your sample mean gives you the lower limit of the estimate. That's this one. And 1.96 above that mean gives you that upper limit of the estimate. So the area of probability of you basically having that population mean contained is 95%. 2.5 to the left, 2.5 to the right. And this is your margin of error. So if you are quantifying now, whatever you want to quantify, you can quantify that 95% confidence interval, and you can say, if this is indeed a representative sample, this should contain the population mean. If it's not, and it's a biased sample, then it does not. But then I have means, and that's what we will do today. I have means to quantify that and compare that to the population mean. And then I will know it's not representative. So that's the margin of error around a point estimate, which is the mean of your sample data. So using the normal distribution works if either the sigma is known or when we have a very large sample. So sample size definitely kind of determines whether you can use the normal distribution safely, or you need a t-distribution, or the sigma is known. The sigma is the population standard deviation. Otherwise, you would need to estimate it. If it's smaller, you should use a t-distribution. So now you have 3 different of these confidence intervals that are commonly used. So when you think about it, you're capturing that confidence around your mean estimate. And you're saying, okay, so based on that, yes.
So you said smaller, we have to use the same distribution.
Yes.
So how do we know it's smaller? Like,
well, we're getting there. We're getting there. We're doing t-distribution once we have finalized the confidence intervals. So for the sake of argument, let's say we know now our sigma. So we know our standard deviation and we're working with the C distribution. But we're getting to the D distribution next. And it's an interesting story why somebody actually came up with the T distribution. Okay, so the sample mean plus minus 1.96, the standard error of the mean, that's the 95% confidence interval. If you are now, so let's assume you want to be more confident about something. When would you be more confident to contain the population mean? When you extend your confidence intervals. So the wider the confidence interval, the more certain you are, you capture that population mean, right? If you make it narrower, then you're basically less certain. So three commonly used confidence intervals are the 90% confidence interval, the 95% confidence interval, because the alpha level, the p-value of interest is, and whoever has read a scientific publication, you know that p-value at 5%. That's like, since Fisher came up with this in the 1960s, is like the holy grail for every scientist. So essentially you have the 95% CI, and then you have the 99% CI, which is 2.5 times the standard error, plus and minus from the mean. So that gives you this confidence interval. You can also make this any individual sample mean or confidence interval. You could hypothetically have a 73% confidence interval, and nobody can say anything against that. It's just not really insightful. So, but basically you always have sample mean plus minus a set of alpha half. Alpha is your 5% threshold, or it's your 1% threshold for 99% confidence interval. So it's basically your type 1 error. That's alpha.
What is that?
That? That?
Yeah.
That is alpha.
See, what I mean, what is the D?
Oh, the C is the set score. The set score is 1.96. Remember, minus 1.96 and plus 1.96. So that's the set score. So I'm calling it set because whenever I say C, nobody understands whether I talk about C like Caesar or C like zebra. So it's like I'm notorious for that. So that's why I'm embrace set. Okay, so set of alpha half, because alpha in its totality is the type 1 error, that's 5%. So you want 2.5% on each side, that's alpha half. So that's that set. That's minus 1.96 or plus 1.96 for the 5% alpha. And this is how simple it is. It's basically alpha is 1 minus the confidence interval. So your alpha is basically defined by the confidence interval. You can do this either with a continuous variable, or you can do this with a binary variable with your proportion using the normal approximation. Same principle, same approach. We will do it today in R. So that's where it's kind of becoming a practical example. The importance is that you do not confuse the 95% confidence interval with the set score. That distinction is important. It follows the same standardization procedure, but it has a different implication. It has a different interpretation. So it does not contain 95% of all the population values. That's the set score in the population. And it does not account for the bias in the point estimate. It accounts for the bias of that actual sample. So if that sample is biased, but it doesn't necessarily mean that it's the only way to quantify a bias. It's not, it gives you an idea of the bias. The 95% CI does provide an interval in which we are 95% confidence that the true sample mean, mu, lies, and that it contains the true mu, the true sample mean, in 19 out of 20 random samples. Assume mu to be known but unknown. So if you don't know the population mean, you are essentially, you're tapping in the dark. So you're 95% confidence interval, you only know it for your sample mean. So it becomes a marker of you essentially using this for different purposes. The 95% confidence interval will be super useful when it comes to regression, when it comes to sample comparison. When you compare, for example, you compare, let's say, a before and after comparison. You're testing against the null hypothesis that there's no change from before to after. So your 95% confidence interval helps you for hypothesis testing against a mean estimate of 0, which is basically a difference of 0 is no change from before to after. So if you have a 95% confidence interval, which is not containing 0, you know your mean difference is different from 0. So it's basically with an alpha of 5%, you can test it against a mean change of 0. But we'll get to that later. So if we take repeated samples and constructed a 95% CI around every sample mean, then 95% of these intervals would contain the true population mean if the sample is unbiased. 5% would not contain the true population mean. And this is the $1 million depiction, which basically shows that. Let's assume that this blue line is the mu. That's the true population mean. And your sample would be expected to contain this population mean if it were indeed the representative sample. So now you're calculating now 100 samples, and basically 5 of those are not containing that mean. So that means essentially you have a biased sample. So this is how you have to look at this. So each of these confidence intervals basically is meant with a 95% certainty to contain the population mean. And that's a very nice depiction of what you're trying to do. So it's a probability. It's actually, again, a probability based on the frequency. So the $1 million questions, is a 99% confidence interval larger or smaller than a 95% confidence interval? It's larger, exactly, because you're extending the probability that you contain. Yeah, exactly.
1%.
Yeah, exactly. So you have, exactly, you only have 0.5, so it's 2.58 instead of 1.96. If you have a 90% confidence interval, you only have 1.65. So it's actually smaller and narrower. As the size of a CI increases, does the confidence increase or decrease? Same question in different package, right? What does the CI tell us about the variability of individuals in the population? Nothing. So now back to that example with the birth weight of infants. So we have now 119, and this is a nice example that you can kind of try to do some calculations. So basically have 119.6 ounces plus minus 1.96 multiplied by 1.035. That's the standard error of the mean. You basically get to 119 plus minus 2.03. You're adding that and you're subtracting that, and you get your lower and upper limit. You're doing the same with a larger sample size. You basically, what you see is what we discussed before. You see that the denominator increases, the standard error decreases. Consequently, your estimates, interval estimates, are also getting narrower. So you can narrow it in. And the same you're doing also when you then extend your 99% CI, or your CI to 99%, you're basically getting a wider range again. And now, but this requires for you to know the standard deviation now. And that's the standard deviation of your population that in practice, nobody knows. That's the issue, right? It's like, who has ever measured the blood pressure of every single New Yorker? That is just a number that's unknown. So now, obviously, a lot of other people have had the same issue, and so did the Guinness Brewery. So one of the good things that beer brought to this planet was at the tea distribution, where Gossett, he was the chief brewer of the Guinness Brewery in, I don't know when he came up with it. I think it was at the end of the 19th century. So he basically figured out, so he was facing the following problem. You have a quality criterion on a beer that you want to reach. I don't know what exactly it is. I'm not an expert in beer. But basically, so you have a quality criterion that you want to meet. And so now the brewery is brewing and brewing and brewing and filling it in bottles. You cannot test every single bottle that you're producing in a day. If this is a couple of 100,000 bottles, you can't test anybody. So he came up with the idea to basically only test little batches, random samples of your beer. So you know the variability within the samples, and then you can use these approximation to estimate the variability in the overall population. And then you can make assumptions about that brewery for that particular hour or for that particular day. And you can draw inferences based on that. How much he did choose? I don't know how much beer they tried. I have no idea. But this is how they came up with the principle, right? And it's basically the same. We talked last time when it came to diagnostic testing, we talked about pool testing. You're doing the same thing. You take small little samples out of a population like New York City. You test these samples for COVID. You know the prevalence in your little sample, and you can extrapolate this to the population. And this is where confidence intervals and the central limit theorem allows you to actually extrapolate it to a larger population. Yes.
Same happens like in our country when we have import of drugs in medicine.
What?
Import of medicine.
Import of medicine.
Yeah.
Okay.
Every time drug agency takes 3 samples from like without choosing how to say this. Yeah,
Okay.
randomly, and test if it's matching. So everything is okay. They will allow.
Okay. Yes. Yes. That's random sampling. Yes.
Yeah.
Goes in the same direction. Goes in the same direction. Yeah. It's the same principle in a way. You're basically estimating variability in an overall population of whatever the product is. This is also with product testing. Whatever the product testing is, whether it's beer, I don't know, cars, you name it. Whatever you want to test, the same principle applies. The variability is basically to be extrapolated on the overall population, and the variability of your sample, if sampled correctly, allows you to draw inferences of your overall population.
So, but maybe there should be some number with a big population. How much should be this? Like how much samples you can choose?
Oh yeah, so there are quality control criteria. Yeah, so if it comes to that depends on how much the usual to be expected variability is. I don't know how much the quality criterion varied, but likely you will have tighter controls and higher granularity of sampling if you are more likely to see deviations from what you actually want to get your quality at. So it's definitely affected by many levels, but I'm not a quality control expert. I'm not qualified to talk about that much. I just can tell you a bit about variability. But basically, this is the direction you have to think when it comes to population variability and sample variability. And that's the relationship. That's really interesting. Good. So now we talked briefly about, we talked briefly about population standard deviation and population standard deviation unknown. So that becomes the T. And the T is a little different because the T is calculated based on an S rather than a sigma. So if you remember the sigma we calculated, we looked at the formula, it's the deviation of each individual entry from the mean, squaring each individual deviation, adding it up to a sum of squares, dividing it by the number of entries gets you to a variance. And the variance square rooted gets you to standard deviation. So it's kind of the standardized deviation from the mean. So now the T is a little different because the T uses now the standard error of the mean calculated by the S. And the S is now the sum of squares. So again, deviations, squared deviations, added up, sum of squares, divided by the degrees of freedom. The degrees of freedom is your sample size minus 1, and I'm not going to go any deeper, but basically you're dropping one redundant variable. You have the sum of squares, and you have all entries for your variable. Minus 1, you can drop 1, because that relationship between sum of squares and all other variables minus 1 will not change. So the last dropped entry in your data set can be dropped because it can be derived from the sum of squares, the actual observed variability, and all other entries but that one. You don't need that one. You drop the redundant. I'm not going to go deep into the philosophy behind it because, yeah. So somebody came up with that because you needed a way to inflate, irrespective of sample size, you needed to be able to inflate your estimate for the variability. And you're doing that because the t distribution means to resemble the normal distribution, but it's actually narrower. And it's dependent on how much entries you actually have in your sample. So it's dependent on the sample size, and you basically need to inflate it by an undetermined value that is following a linear equation. Let's just take it. It's degrees of freedom rather than sample size. Okay, standard error of the, we talked about this, the t, normal, yep. One way of depicting this is whenever you talk about normal distribution, you basically, you have always first the mean, then the sigma. This is how you calculate the t. And this is also different. So the normal distribution is one normal distribution. The t distribution is n different distributions. So there's a different distribution, there's a different function for each sample size, for each degree of freedom, which is n minus 1. So that means you have a different function each time. That's why a t-score table as compared to a z-score table, and I need to upload this t-score table. No. Why are you doing that? You're not supposed to do it. So a t-score table looks different than a z-score table. T-score table looks different than a z-score table, and it looks like this. So you have different functions. So all of these functions, the frequency polygon at the normal distribution is a mathematical function, utilizing the mean and the sigma. Each of these degrees of freedom describes a different function, which means your 5% threshold, which is 2.5 on each side, is not 1.96 for each function. It's a different value for each function. That's why the table looks different. So for each degree of freedom, you would need to find a different value. So it's now not anymore a 1.96 multiplied by t. It's not that easy anymore. This is only possible with Z. It's now 2.31 multiplied by t. It's 2.23 multiplied by t. So this is how you determine confidence intervals in a t distribution. You don't need to do this by hand. R is doing this for you, but I'm just telling you it's different based on each individual degree of freedom. So, but now let's go back to this. But this is what is meant with like, there's a different distribution for each sample size. It's different thresholds. They're changing based on the sample size, but it's an approximation of the normal distribution. That's why you're doing it. Good. Higher degrees of freedom, the narrower the spread of the t distribution because it's narrowing down. That's the t-score table. We just looked at this. Degrees of freedom is a number of independence observation minus the number of parameters estimated during intermediate steps. So that's basically the number of variables you have. Knowing the value of statistic df is n minus the number of observations that could be recovered if lost. That's so you have the sum of squares. You drop one value, you can recover that one value. Good. The calculation of the confidence interval here is the same. You have the sample mean x bar plus minus t, critical t, degree of freedom dependent or sample size dependent for half alpha half multiplied by s. That's the estimated standard deviation divided by the square root of the n. That's your standard error of the mean. So back to alcohol. So you quantify that alcohol content. You basically have different beers that basically all lead you to one quality criterion, and you do sample batches to estimate that, and you know the variability. So no beer that you will have exact one exact content of alcohol. And that's true for whatever car you buy, whatever car tire you buy. None of them will exactly be that size that you expect. There is going to be a manufacturing error in there that has variability. And all of this is quantified again with t-distributions. Yeah. So assumption is it comes from a statistically random sample, which is not always true. It's normally distributed because all of this is a so-called parametric test. Parametric tests are tests that are testing a normal distribution, and the assumption is this is a normal distribution that I'm analyzing, as compared to non-parametric tests, which is basically not a normal distribution, or you don't make assumptions about the distribution. And yeah, so these are the two assumptions, the two main assumptions. Statistical inference is called robust if the outcome is not sensitive to violations of these assumptions made. That means that if you are analyzing data that is not normally distributed, but you're using a parametric test, using a t-test on non-normally distributed data, you're making a much more conservative estimate. That means you don't see a difference between two samples that you're testing and the data is not normally distributed. You make a very robust assumption if you see a difference. If you don't see a difference, you may consider using a non-parametric test and still see a significant difference without actually committing a type 1 error. So that's important to keep in mind. So two-sided t-procedures are robust against non-normality of the population, except in case of outliers or strong skewness. Two-sided t-procedure, yes. So two-sided is always more conservative because essentially you have smaller estimates, particularly with skewed data. If it skews in one direction, you may be more likely to see a difference, but we'll get to that later. T-procedures are more conservative. Yeah. Statistical sample, yeah. So I said before that the normal distribution and the t-distribution are basically identical when it comes to a sample size of 500. Statisticians to some extent, they give you a little bit of freeway by saying if you reach 30 in your sample size, you're kind of getting away with using a normal distribution. So if you use 1.96 with a sample size of 30, you're kind of all right using 1.96 or minus 1.96 here. Why is that? Well, if you look at the t-distribution, you're seeing here that the 5% thresholds here are varying quite a bit, right? So you see here that your 5% threshold here is 4.3 times the t. That gives you the 95% confidence interval. 4.3 versus 1.96 in a normal distribution. The further you go down and you increase the sample size, that interval is getting narrower and narrower and narrower. So you're getting actually easier. It's easier for you to get more confident about your interval. And if you're here at 500, it's 1.96. If you go back to 30, you're confident at 2.04. 2.04 versus 1.96, that's a 0.08 difference. So that's kind of forgivable. It's a rule of thumb. It's not hammered in stone. It's something you get away with. If you would say, okay, so I have a sample of 32 individuals that I've studied. I'm using 1.96 to estimate my confidence interval. You get away with it. And it doesn't really make a difference because it's in practical terms, it will not be much of a difference. So it's statistics. Statistics is not always accurate. It deals with probabilities. What's common is common, what's not common is not common. Okay, this is robustness. The most important thing is really that you always have a simple random sample. That is really, that's the assumption you're not getting away from. Okay, Q for t-distribution. When estimating a standard deviation from the sample, instead of knowing it from the population, we use the t-distribution. Yes. The 95% CI is larger, smaller when using the t-distribution than when using a set. We've just seen it, it's wider. So the t-distribution is wider. So the CI is actually larger. As the n increases, the t-based CI becomes more similar than the set-based CI. That is true. At 500, it's identical. After 500, it's identical. CI is given high as the so okay, confidence interval gives you an interval is likely to contain the true population mean, age, cholesterol, whatever normally distributed parameter you have. The high confidence requires a large margin of error. So the wider this is, the larger your confidence. But the margin of error that you're assuming is actually larger. Your best point estimate from a sample is at the middle of the CI. So that's your best estimate. That's a point estimate. The standard error and the CI tell you nothing about variability in the population. That's important to keep. It doesn't tell you anything, but it's affected by the variability, because the variability of the population will affect the variability of your mean estimates and your assumed standard error of the mean, the variability of your mean estimates that you're assuming. And the t-distribution is used for small samples where you utilize the t-distribution, the variability in the sample to estimate the variability in the population. Good. So, any questions on this? I think it's kind of, it's simple, but I think there's really value to understand this really in a very comprehensive manner, because you hear confidence interval, confidence estimates, sample mean estimates versus population means. You hear that quite frequent, and you will hear that more frequent in this class. And so there, I think there's value to repeating all of this. And to bring it also into practice, because we're going to bring this now into practice in an R example, which will essentially be a very quick one. And at 7, we can then start taking the quiz. And then you can do the graded lab 1 at home, which essentially bases code-wise on the practice lab 5. And you just have to alter it. And you will see, were you able, Nathania, were you able to download the new practice lab 5?
Oh.
I put the updated one up. So it should be super easy to do graded lab 1 based on practice lab 5. So that code will be super easy to adapt. Okay. All right. Any questions on Zoom? Oh. Do you have questions on Zoom, or was that? Yep, good. Okay, so I take this as no. Okay, so now you have on Canvas. That was a nice sound. Okay, so you have on Canvas 2 files, 3 files. You have practice lab 5, which is today's exercise. You have practice lab 5, the R code, which is the code leading you to finalize practice lab 5. And then you have graded lab 1, and graded lab 1 is not really that much different from practice lab 5, but it will require you to adapt the code to what is being asked for in graded lab 1. But it's autodidactic. So I would like for you to very much label it as in the same fashion as we're labeling the practice lab with your name, graded lab 1 instead of practice lab 5. I also want you to please enter your name in the code. So just write at the beginning, graded lab 1 with hashtag. Don't forget, hashtag is commenting out, and make sure that you hashtag your name and graded lab 1 out. But just have it in the code. Okay?
That's
Yes.
line.
First line, yes. first line you program yourself is gonna be hashtag your name, hashtag created lab 1. Okay, but practice lab 1, let's quickly get through that. Practice lab 5, not 1, sorry. Okay, so we're basically, I explicitly took now enhanced data. So this is the enhanced data set that you also will be using for the final project. So the only thing you need to do, in case you didn't open it yet, you will need to install the package enhance. If not, you just go on line 4 and you run line 4. This will install and will activate library enhance. Then you run line 5. That is basically now opening the data. Now you have all these variables in your enhanced data set, and then you just push it into a data frame enhance. That gives you 6,779 observations of 76 variables. Then you also load library enhance A. That just gives you even more variables. So you have quite a number of variables available. And you have dietary interviews, you have spirometry data, you have bronchodilator administration, you have dermatology results. So the enhance is really, it's like a paradise of different variables. Good. So now we want to do descriptive statistics. So we're taking not just the enhanced data with str. Please remember this command. Str is investigating the data set. Basically gives you a characterization of the data set. Gives you exactly information on what the data looks like. It tells you it's numeric. It has a factor. It's an integer, or it's a character, which you then have to relabel. If you have factors with 5 levels, you can recode this into different variables. So it gives you an overview. So we are now, as per practice lab 5, we are now interested in age. So we're doing an analysis of age and biological sex, only of the first 200 individuals. So first we want to do descriptive statistics of the full data set. We're assuming that it's the enhanced population and we're sampling from the enhanced population. And we want to know whether we have a biased sample or we have a representative sample. You remember how we did Ames, the Ames data, the Ames, Iowa, we did the living room. We created samples, random samples that were somewhat representative of the overall population of living rooms in Ames, Iowa. So now we're going to do this a little different. Now we're going to take something which has a higher probability of actually creating a biased sample because we're just taking the first 200 participants. That essentially is easily done by taking enhance. And we're saying now, so enhance, if you address things with a $sign, enhance and the variable name, you get enhance $ID. That basically then becomes a vector. If you take this vector, you take the brackets, you basically was 1 to 200, you only take the first 200 entries, right? You remember that. So now we're creating a data frame, and I'm trying to make it a little larger. Okay. Okay, that's a little larger. So if we're taking the first 200 entries here, so we're creating a data frame, df data.frame ID. This is what we're querying from the enhanced data set. We're taking only the first 200. Age, same thing, we're only taking the first 200. So it keeps the alignment. It just literally queries these 3 variables, only the first 200, and merges them together and pushes them over in a new data frame, right? So if we're running all of this, we're basically getting a data frame that is 200 entries long and contains 3 variables. So what am I doing? I do ID, I do age, And I do here an if else. We remember if else, right? If else is just recoding it right on the spot. So basically it says, okay, so if gender is now male, then give me a 1. If it's not male, then give me a 0. So basically it's only querying and recoding it into male sex, yes, no. 0 or 1, yes or no. So now we want next, we're gonna create here a factor. A factor is basically how R looks into binary or generally categorical variables. And you with factor, you can now relabel it. So you have male sex. You have with male sex, you have either 0 or you have a 1. Male sex 0 means not a male. Since we're talking about biological sex, we only have a male and female. So it's basically a 0 is here a female, a 1 is a male. Labels, we're labeling this as female and male. Female for 0, male for 1. Okay? Good. So we're doing this. And what the beauty is, if you recode this into a factor, if you do summary DFH, that gives you, okay, so that's the summary of age. No. Yeah. Now the beauty of this is actually if you do summary DF male sex factor, it will automatically do the counting for you. It recognizes, so it takes the binary coding and it automatically counts and treats this as a factor. So it knows it's a categorical variable and it will treat it as such. Okay, so here are the descriptives. So test the representativeness of your samples to the overall population, computing the margin of error and the 90, 95, and 99% confidence interval. So that's simple, right? So we know 90% confidence interval 1.65, 95% confidence interval 1.96, and 99% confidence interval, that's the widest one, is 2.58. Good. So I only did standard error of the mean multiplied by age, that's 1.96. You can, in the graded lab, you can do the other 3. So that's simple. But basically what you do, you take the standard deviation, and keep in mind, since the sample is greater than 30, I'm using a normal approximation and I'm using basically 1.96. I assume this is normal enough. So if SEMH is now calculated, now I'm missing this. Okay. So SEMH is now standard deviation. Is now standard deviation divided by square root of the length of DFH. So the length of DFH, that's our n, right? So we are counting by calculating the length of a vector, and that gives us 200. So this is now the standard deviation of h of our data frame. That's 21.97 divided by square root of the length of DFH. So now if we want to know now our lower limit of the 95% confidence interval, we need to calculate mean of DFH minus the standard error of the mean h multiplied by 1.96, right? If we want to do the same for the upper limit, we do mean plus 1.96 multiplied by the standard error of the mean. Same story, simple. So standard error of the mean, h, and now with the paste function, we can kind of display this nicely. But that's just playing around, right? So we're basically we're just pasting it and we make it in a analyzable format. So we have now paste, and that gives us 38.4. 95% CI, 35.4 to 41.5. So that's our 95% confidence interval. So now if we keep in mind our mean of the population, how much was that again? The mean of age was 35. So what do we compute out of that? We're actually containing our population mean. So maybe our sample is not that terribly biased. Yes.
What is said age representing?
SEMH is the standard error of the mean.
Oh,
That is the standard deviation divided by the square root of the length of DFH. So that's length. So now next we're being asked to depict the distribution of a sample for the continuous data with the confidence intervals in a histogram. We're doing this here. We're building a histogram. That's the histogram. Doesn't look very normally distributed. Now we do another histogram. That's again DFH. Why is it not normally distributed? Because it has constraints. It starts with 18 and it ends with 80. And that's a privacy thing. So now we have abline of DFH. That's now our mean. And now we have a second one, which basically gives us the confidence interval on the side. Now we want to also show our population mean. We're doing this with another one. So that's basically a green line now, which you see here. So that's how you can all add to that histogram. Now you want to depict the data of a continuous variable of the sample in a box whisker plot. We're doing that with box plot. That's a box plot. We're doing this with two box plots, which is now just taking the factor into account. And that's actually the beauty. So if you do a continuous variable and you want to show it as a function of different factors, you show this with your factor and you're separating this with the tilde. The tilde basically will distinguish this continuous variable between these two different factors. So that allows you to basically bring this over. Okay, so any questions with that? I think it's considerably simple as a code. What we're doing now is the last point. So we want to put this now in an HTML format. And now we're going to go a little deeper into how we can utilize R. So in the end of the day, when you look at an R code and you want to present, let's say you want to create a report. You did a clinical study or you've been involved in some shape or form with a clinical study. You want to analyze some simple data. You want to show some data in any form of report. You don't want to have these outputs somewhere and copy the console over like I ask you to do for the practice labs, right? This is not really something you want to show somebody. That's not really PowerPoint format. That's not nice. So therefore, R has come up with a simple solution. So you can do it the fancy way. You can use R basically with a package and additional plugin that you would need to install that I spare you with because it's a little trickier than it is, but we will get to it later. You can utilize in R a particular function that is called markdown. Markdown. Markdown.
What's it for Windows? For Windows?
No, it's for R. It's in R and it's easily to be started by going on new file. And there's something that can be selected, which is R Markdown. If you do this, it will ask you here various things. It will ask you for a title. It will ask you your output format. Do you want HTML, PDF, or Word? You will label this practice lab BTM6000, practice lab 5, and your family name. You can give it a date or not, and then you select HTML. You can select PDF. The problem is you need that. So I don't know who of you is familiar with LaTeX. LaTeX is basically, it's a way to code a PDF document. So you're basically writing and you are coding into how do you want it to be presented? Like you had a computer science background, right? You must have used LaTeX in some shape or form, right?
I don't personally.
Okay, but you heard the name. So it's quite commonly found. Hmm?
I skipped down the road, it must have added the HTML pages.
Okay, that's okay. Many people know it that way. So that it can be a little bit tricky because you need to know how to handle it. And I personally am not a LaTeX programmer. I don't use it. I have friends that use it in various forms. They're basically when they're writing a paper, you don't get a Word document, you get a PDF document because they're programming it in LaTeX. They're writing everything in LaTeX and they're basically exporting it into PDF right away. Which is when you collaboratively working with somebody and you don't read LaTeX, you need to comment everything out in a PDF document, can be quite a challenge. But yeah, so that's one of the advantages with Word. Okay, we are sticking now with HTML for now. We will use a package to basically create also PDFs later. So you will also learn how to do PDFs. That's quite simple. Okay. So we're clicking OK on HTML, and then we're getting this. What we're getting here is a pre-formed markdown document. So all of this is basically, this is already markdown. So we have here the title, the output, the date, and we have here what is called a chunk. A chunk is basically a little snippet of code. This is where the R code goes into. So it will recognize, Markdown recognizes this as an R part. So it knows that's what's coming after these 3 apostrophes, that curly bracket. And whatever you write in there, you can label these chunks. You don't have to label them. And we're going to take include false out because that would mean it doesn't show the code. We want to see the code. Everything after that will be R code. That was outside here, R markdown with 2 hashtags, that's the heading. If you take one hashtag away and you only put 1 hashtag, then it's a larger heading. And the way you're putting this all together is by clicking on knit. So here you can knit it to an HTML, you can knit it to a PDF, and you can knit it to a Word document. Basically, we're knitting. And we're basically creating now our first HTML document. And since it's pre-programmed, you just have to find a location where you want to save it. And then you can just save it in this location. So I'm going in module 5. That's my folder here. I create now an output folder in my folder. And now I'm just saving this in there. So that's BTM6000. Which option? Yes, you should have knit. You don't have knit? No, you should have knit. Oh, right there. No, here, knit. Yeah, knit too. Okay, now find where you want to save it. It's just Windows and Mac. It's a little different. Not a big deal. So now you create lab 5, practice lab 5. 5. And family name. Okay, good. Output. We're saving this in there. And now you see already, so here it's already working. And it's basically creating your first HTML file. So that's exactly what R has pre-programmed. This is the cast data set, which is like one of the sample data set it shows. So you basically created this now automatically in the HTML file. So now we want to use this to.
All graphs there.
We
have all graphs there.
You can put the graphs in there. You can put everything in there. So that's how fabulous this is. And you can do this by literally copying this over from your R code, and it will run you exactly that down. It's nice, right? And you can make the chunks disappear, that it doesn't show the actual R code. and you just see the graphs, you just see the writing, you can copy text in there, you can explain what you're seeing, and you can all do all of this in HTML. It's super useful.
This is a regular HTML document, like you just create an HTML document from like on Notepad.
On what? On a notepad?
On like some program that isn't RStudio. And then you just,
Yeah, but while RStudio is running the analysis, right?
right,
So you would need to, you could hypothetically, you can do this, the HTML editors, you can take the graph, if you exported a graph as a PNG or as a JPEG, you can import it into an HTML editor.
RStudio to render the R code.
It's actually Markdown.
Yeah, but there is R code.
There is R code, yeah. No, you can use various ways how to do that. But yeah, there are HTML editors that you can create HTMLs. I'm just not a very expert in HTML editing, but yeah, there are different ways to do this. This is just, it's a user-friendly way how to do this in R. That's why I'm showing you, because there are just ways, there are really nice ways how to utilize R to create documents, create reports, you can write a thesis in there hypothetically. I wouldn't recommend it. It's hypothetically doable.
We have only one slot here.
No, that's only the brief form. So we're populating this now. So we have 10 more minutes. We're gonna copy our stuff now over. So we're closing this now, because we don't need this. Whatever the output is, that's basically just the end product. We don't care for that, because whatever we're running in Markdown, that's actually what our work is. You can recode all of this. It's not like Word where you're writing in Word, you're writing in the code, and the output of that code is actually your end product. So if you were to bring that over now, so let's copy here 1 to, let's say 1 to 16, we're copying over now in the first chunk. And here we do include equals false, because we don't need to see the code for the data preparation, right? So we're copying this in. Now we're deleting this. We're going now into taking the compute descriptive statistics for the full data set. This is 18 to 22. We're copying this over, putting this in our actual file, and we're bringing this out into actually serving our analysis here. So we're leaving this now without the cars. So if we click on Knit now, we're getting now a whole different story. Okay, so this was not good, because now it takes a while. So that's a built-in data set. So you have different built-in data sets. R is full of built-in data sets. You have like data, you have passenger lists of the Titanic on there. So you have like a million things. Titanic caught timeline of the submarine, but it's basically you have a million things in there. So we have compute descriptive statistics. Then we have, now we're creating, copying this over, and you can create this new chunks easily with just copying over the apostrophes. Just delete here pressure, echo equals false. Be careful with include equals false and echo equals false, because that takes off the actual code, the computed code. We want to see the code in the HTML file. Right? So with echo, so include equals false doesn't show neither the code, nor does it show how R actually, what error messages R gave you back, or whatever processing commands or documentation R was actually showing. With echo false, you're only taking the R responses off, but you leave the actual code in there. So echo equals false is actually not that terrible. We are taking this all off, and we're now, oops, now we do create a data frame, create a data set. We're putting this up here. Don't forget, you still need to do the 90 and 99% confidence interval too. So this is here to be added. Okay, I'm going to do this and this. So now we do mean age and this. So you will have time, you can play around with this in peace at home. So this is now normal approximation. Now we're just taking the rest down there for the sake of time because we need to get to the quiz. Okay. So this is now the whole thing. The beauty also, if you do knit, it will automatically save the RMD file. So the RMD file, so you have the ending .r, that's the R file, that's a script. .rmd is now an R markdown file. So that contains these chunks and the apostrophes that indicates this is a markdown file. So if you're just running this down now, if you're running this whole thing down now, you will get now an HTML file containing the histograms, containing the box plots, and all of this, what we did. And it's this now. Okay, so here are the variables. That's the histogram. That's the histogram of the data set. That's the box plot. That's the box plot. Here you also have our 99% confidence interval. So that's not a 99% confidence interval of our population of males. So we have 50% males in there. So it's 99 is our value or estimate for the male population.
Number of.
That's the number of individuals out of our 200 individuals. 99 are males. So there's a prevalence of
49%. 49%, right?
Yep. Yes, you're right. Well, yeah.
5%.
Yes. Where did you see them?
Number is,
Yeah.
down.
Oh, yeah. 49.6 and 49.6% now. Okay. So here this and the box plots. Yeah, and this is saved already, so you're all done essentially. And the HTML, so you all also CI. Don't forget that, please.
I have the RMD file, but I don't know. Error in. I don't have the HTML.
Knits too? What happens then?
Does it look like this?
Can I have a look? This is as you opened it. Okay, let's start a new one. I need to see whether this is an internal thing. Okay, so HTML. Okay, that's a new one. If we go on knit to HTML, what happens now? Let's call this test now. There's something that you may have entered that kind of, no problem. Okay, any questions here in the classroom? Any questions on Zoom? Do you have any questions on Zoom? Shay, Talia?
No questions.
No questions? Okay, I hope you agree that it's really quite powerful to utilize R in that regard. I think it's really can be very helpful. Okay, so this being said, I think we can turn now to the quiz and quickly do the quiz.
What if we do it next?
No. Well, then you're gonna do